Greetings, Math 347 fans. This video will be having a look at solutions of non-homogeneous differential equations. This is part one of two videos on this topic. The second part will cover applications of non-homogeneous differential equations. Okay, so in this video we're going to talk about the structure of the solution, and then we'll talk about the method by which we find the solution of these non-homogeneous differential equations. So here's the overview. We're having a look at the second order constant coefficient differential equation. We know how to solve the constant coefficient version, which we'll represent as Lx equals 0. Now we're going to turn our attention to the non-homogeneous version called Lx equals f. You might not be surprised to know that the solution of the non-homogeneous equation is related to the solution of the homogeneous equation, and we'll see that in just a second. Generally speaking, the function f is called a source term. This is motivated by the study of the related forced damp spring system. So in this cartoon, we're imagining a mass spring system like we had before, spring constant K, damping constant gamma, x of t representing the distance from equilibrium position, and we're adding to that one new force, which is that there's an external force, little f of t, that acts on the spring as a function of time. So you can imagine that we can do the same thing that we did before to come up with a differential equation that models this forced mass spring system. Go ahead and apply Newton's second law, and the only change is that the new external force is given by f of t. Okay, so we see that here, and the new differential equation for the position function, the unknown function x of t, is given by mx double prime is the sum of those forces. So there's a force corresponding to the spring force, a force corresponding to the damping force, and also a force corresponding to the external force. Okay, so rewriting this in sort of our general format, we have a non-homogeneous second order constant coefficient differential equation of the flavor mx double prime plus gamma x prime plus kx is f of t. And if we specify initial position and velocity x naught and v naught respectively, we have a properly formed initial value problem. Okay, so let's go ahead and talk about the structure of this solution. Again, we're using our differential operator notation. Lx is defined to be ax double prime plus bx prime plus cx. And we're going to go ahead and call x sub h any solution of the homogeneous equation, and x sub p a particular solution. It turns out that if xh is a solution of the homogeneous equation and xp is a particular solution, then xh plus xp is always a solution of the homogeneous equation. And you can see this just by plugging in that sum into our differential equation, which once again we'll represent here by operating on the sum with L. So of course, L acting on xh plus xp by linearity is Lxh plus Lxp. Now we know that xh is a solution of the homogeneous equation, so it pops out 0. On the other hand, we know that xp is the solution of the non-homogeneous equation, so it pops out f of t, and we can see that the equation itself yields Lx equals s. It's a solution of Lx equals f. Okay, this is like something that we recognize from linear algebra. The fact from linear algebra is that if you have a particular solution, a solution of ax equals b, a non-homogeneous equation, then you can always add any element from the null space of the matrix, and that will be a new solution. Okay, so same idea here. We're sort of adding an element from the null space, and we're calling it a solution of the corresponding homogeneous equation. Okay, second fact is the structure of the general solution. So the general solution to Lx equals f is always c1 x1 plus c2 x2, where x1 and x2 are a fundamental set of solutions to the corresponding homogeneous equation, and plus xp, where xp is a particular solution. So to see this, we'll just make the change variables that u is x minus xp. Then we can see that Lu satisfies a homogeneous equation. Now, we know how to solve a homogeneous equation. we can just find a fundamental set of solutions to that homogeneous equation and write the general solution to the homogeneous equation as C1x1 plus C2x2. And if U is C1x1 plus C2x2, then we can see that x, of course, is just C1x1 plus C2x2 plus x sub p. Okay, this reminds us of a fact from linear algebra 2, namely that the general solution to ax equals b is a linear combination of n plus 1 vectors, where one of those vectors is a solution to the non-homogeneous equation, and the other n are the basis for the null space of the matrix A. Okay, so this is sort of the same idea here. In our case, the linear operator L has a two-dimensional null space, so that x1 and x2 are a basis for that null space. Okay, the good news here is that this gives us a strategy for finding the general solution of the non-homogeneous equation. And that strategy revolves around first solving the homogeneous equation. So the first thing we have to do to solve the non-homogeneous equation is find a fundamental set of solutions to the corresponding homogeneous equation. Okay, so again, here I'm calling that F. And once we find a fundamental set of solutions to the homogeneous equation, we're going to write down the solution to the corresponding homogeneous equation and just call that x sub h. So x sub h is C1x1 plus C2x2. Then the last thing to do is to find any particular solution, and it turns out any particular solution will do. Once we have a particular solution, we can take the general solution to the non-homogeneous equation to be C1x1 plus C2x2 plus that particular solution. So we know how to find x1 and x2. That was material from the last section. In this video, we'll see how to find a particular solution. So how to solve for a solution of the non-homogeneous equation, which will give us ultimately the general solution of the non-homogeneous equation. Okay, a couple more facts about non-homogeneous superposition. So if we want to find a particular solution to Lx equals f, where the source term is given by f of t equals k g of t, and we know how to solve Lx equals g of t, so we know, for instance, that there's a particular solution xp that pops out g of t, then it turns out linearity tells us that there's a particular solution kxp that pops out f of t. Okay, so this is using a constant multiple in and out of our linear operator to our advantage. And the same thing works for sums. So if we want to solve Lx equals f, where the source term f is given by a sum, we can use a same idea here, namely that if Lxp1 gives us g and G1 and Lxp2 gives us g2, then the sum of xp1 plus xp2 pops us out f of t. Okay, so again, that's useful because oftentimes it'll allow us to break problems down and solve them in sort of modules and then put the solution together with linearity. Okay, so again, xp1 plus xp2 in this case is a solution of Lx equals f, when f is a sum of two functions for which we know the particular solution. Okay, so again, non-homogeneous superposition. Keep that in mind. It'll come up again here in a minute. Okay, so go ahead and start talking about our method for finding these particular solutions, called the method of undetermined coefficients. The method of undetermined coefficients is again sort of a good guess for a solution that we'll use our intuition to try a solution that ought to make sense. And we'll see that oftentimes that intuition will lead us to the correct particular solution. There will be one glitch in the plan, and we'll address that too and talk about how to resolve things in the case of this glitch. So here's the general idea. The general idea is that we want to find a particular solution of this second order, constant coefficient, non-homogeneous differential equation, Lx equals f of t. So again, the idea here is that Lx is a recipe for mixing up derivatives of some function x, and here we want that recipe to pop us out f of t. So we sort of build our intuition here by asking ourselves, what do we expect for x sub p if the source term happens to be, say, exponential? Well, you would expect to need to mix up a bunch of exponential functions of sort of the same general form to pop out an exponential function. Similarly, if f of t is a polynomial, the derivative of polynomials are polynomials, so we would expect to have to use a polynomial. And it's similar even if f of t is of the form of a sine or a cosine. So we know that derivatives of sine and cosines give us back sines and cosines. So we would expect to have to use some sort of general form of sines and cosines. So here is the method of undetermined coefficients in a nutshell. If the source term f of t is an exponential, we'll try a particular solution that's what I'm going to call a similar general exponential. And we'll see what those two words similar and general mean in a minute. Similarly, if f of t is a bunch of sines and cosines, we'll try an x sub p that looks like a general similar sines and cosines. And finally, if the source term f of t is polynomial, we'll try a general similar polynomial. So just sort of illustrate this method of undetermined coefficients by example, just diving right in. So here is a second order linear constant coefficient differential operator. Lx is given by x double prime plus 3x prime plus 2x, and we want to find first a particular solution of the non-homogeneous equation where the right-hand side is given by e to the 2t. Okay, so again, in order to pop out e to the 2t of Lx, we would have to put in something that looks like e to the 2t to Lx. So this is what I mean by a general similar exponential. We'll try a general similar exponential of the form a e to the 2t. I'll point out as an aside that the fundamental set of solutions to the corresponding homogeneous equation is given by two exponential functions. I won't go through that, but you could easily identify the characteristic equation and the eigenvalues in those two distinct roots of that characteristic equation. Okay, so if x sub p is some unknown constant, an undetermined coefficient times e to the 2t, then we can certainly compute its derivatives. And once we compute its derivatives, we can plug those derivatives in to x double prime plus 3x prime plus 2x. And combining those exponential terms, we see that LXP pops us out 12a e to the 2t. Now, what we want here is for LXP to be e to the 2t, so that tells us that 12a has to be 1, or a has to be 1/12. Okay, so this is the method of undetermined coefficients. We've determined a solution to the corresponding homogeneous equation, and that solution to the non-homogeneous equation is x sub p equals 1/12 e to the 2t. We add to that the solution to the corresponding homogeneous equation, c1 e to the minus 2t plus c2 e to the minus t, and we have the solution of the non-homogeneous differential equation. So again here, this first part is the solution of the corresponding homogeneous equation, x sub h of t, and the second part is the x sub p that we find via the method of undetermined coefficients. Okay, another example, we'll go ahead and have a look at the same differential operator. Lx is x double prime plus 3x prime plus 2x, but here we want to solve Lx equals t squared. Okay, so on the right-hand side, we see a quadratic. We'll go ahead and try a particular solution of the same form, a general, similar polynomial, in this case a quadratic. Okay, so of course, if x sub p is some general quadratic, a t squared plus bt plus c, one thing we can do is find its derivative and its second derivative, plug those in to Lx, and when you do that, it takes a little bit of work, but simplify, 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 plugging in x sub p to the zeroth derivative, the first derivative in the function, and you end up with another polynomial. And in particular, we can see that that polynomial turns out to be a quadratic, right? So it's some quadratic. And here I've just sort of organized our terms in descending order. Okay, now what we'd like for this quadratic is for it to equal t squared, or in other words, we'd like LP to be t squared, or 1t squared, plus 0t plus 0. Okay, so that tells us 2a has to be 1, the coefficient of t, 6a plus 2b, has to be 0, and the constant coefficient also has to be 0. Now, it turns out this takes a little bit of work to solve, but it's not so bad to solve it. We can see that a is 1/2, and it turns out b and c are -3/2 and 7/4 respectively. Those are the undetermined coefficients, and again here we'll express the general solution to the non-homogeneous differential equation as the solution to the corresponding homogeneous equation, x sub h, plus a particular solution that we just found with the method of undetermined coefficients, x sub p. Okay. Another example illustrating the solution using the same differential operator again, but this time we'll go ahead and look at a sine function on the right-hand side. Okay, so once again, if we want to pop out a sine function of this differential equation, we need to be able to put in some sort of general similar form. So the general similar form in this case is xp equals a combination of sine and cosine. So a cosine t plus b sine t. Okay, so once again, we'll go ahead and compute its derivatives, plug those derivatives into the differential equation, find that simplify, 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 and once we do that, we end up with some combination of cosine and sine. And here I've done some simplification here to get a plus 3b cosine t and plus minus 3a plus b sine of t. Now again, what we would like is this for to equal 2 sine of t, or I'll write this as 0 cosine of t, plus 2 sine of t. So just match up the coefficients. A plus 3b has to be 0, and negative 3a plus b has to be 2. Solve that system using your favorite method, and when you do that, you can find that a has to be negative 3/5 and b has to be 1/5, again giving us the solution to the non-homogeneous equation as a combination of the solution to the corresponding homogeneous equation with the particular solution. Okay, and I haven't made a big deal out of this, but all of these general solutions are general solutions in the sense that we can use them to identify the family member to solve an initial value problem. So once you have the general solution to a non-homogeneous differential equation, quick to use that general solution to solve for the C1 and C2 that give us the right initial conditions. Okay, let's go ahead and have a look at a differential equation that's similar to, but a little bit different than the ones we solved. So let's use a particular solution to find the general solution of a non-homogeneous differential equation where the right-hand side is given by a sum of some exponential and a sine function. Now, here we have 2e to the 2t on the right-hand side and sine of t on the right-hand side. Of course, we know the solution in the case where the right-hand side is just plain old e to the 2t, right? We know that plugging in 1/12 e to the 2t pops us out e to the 2t. We just found that. And similarly, we know that that negative 3/5 cosine of t plus 1/5 sine of t pops us out 2 sine of t. Okay, these are things we just found in the last couple of examples. So here we can use linearity actually to go ahead and manipulate the right-hand sides into the thing we want. What we really want on the right-hand side of the exponential is a factor of 2, and what we really don't want on the right-hand side of the sine function is a factor of 2. So here I'm just multiplying both sides of this exponential equation by 2, dividing both sides of this sine equation by 2, and then moving that constant inside to give us the solution to the corresponding non-homogeneous equations. Okay, finally we can put those two together to see that the solution of the non-homogeneous equation in the case of the sum, right? So here we have a sum on the right-hand side, and that solution has to be the sum of those two individual solutions. So I'm calling this xp. This other part, again, is xh, and xp plus xh is the general solution of the non-homogeneous equation. Okay, so in practice, you might be faced with one of these non-homogeneous equations where you haven't already solved for the individual pieces, but you can imagine decomposing it into its modular parts, solving those individually, and then putting the solution back together as you need to. Okay, so the last part of this method of undetermined coefficients illustrates what we'll call the glitch in our method. So the glitch in our method can be illustrated with this example where we're trying to solve for a particular solution where the right-hand side is e to the minus t. Now we'll go ahead and just proceed blindly, again, taking the particular solution to be a general similar form of the right-hand side. So in this case, that general similar form is a e to the minus t. And you can see that when we plug in a e to the minus t, what we actually end up with is 0. In other words, there's no function of the form a e to the minus t such that LP is equal to e to the minus t. Now, if we sit around and look at what we plugged in and look at our fundamental set of solutions and look at what we plugged in and look at our fundamental set of solutions and stare at those for a while, go ahead, press pause, I'll let you. This shouldn't surprise us at all. Okay, so e to the minus t is a solution of the corresponding homogeneous equation. So of course, any constant times that function is a solution too. Okay, so it turns out that a solution of the form a e to the minus t isn't going to work to pop out anything that looks like e to the minus t when e to the minus t is a solution of the homogeneous equation. This is a glitch in the method, and to solve this glitch, we'll go ahead and use our insight from roots of multiplicity. That insight was that when we needed an extra solution and we didn't have one, we got one multiplying by a factor of t. Okay, so we'll do that here too, and multiply the general form of the source term by t until it's linearly independent with all of the members of S, which is again the fundamental set of solutions to Lx equals 0. So you can see that in this particular case, we just need to do that once, and we'll go ahead and start with a solution of the form, again, a e to the minus t, compare to our fundamental set of solutions, and notice that that's going to solve the homogeneous equation, and then amend our guess multiplying by a factor of t. Okay, we know that that won't solve the homogeneous equation. It should give us something interesting. Okay, so here again we've just gone through and computed the 0th, first, and second derivatives. Plug those in to the differential operator, and you can see that when we do that, we get sort of a mess here. But at the end of the day, there's a bunch of stuff that's multiplying t e to the minus t, and there's some other stuff that's just multiplying e to the minus t. And lo and behold, the stuff multiplying t e to the minus t ends up being 0, whereas the stuff multiplying e to the minus t ends up just being, in this case, a. So we can see that plugging in our amended guess, we end up with something of the form Lxp equals a e to the minus t. So here it's quick to see how we need to choose a. All we need to do is choose a to be 1, and that will be the particular solution. Once we have the particular solution, we just add that to the general solution of the corresponding homogeneous equation, and we have then the solution of the non-homogeneous equation. Again, this is the general solution in the sense that we can choose any family member from that two-parameter family to solve the corresponding initial value problem. Okay, one more example, just a fresh example to wrap up this section. Go ahead and outline the solution to x double prime plus 4x prime plus 3x equals 3e to the minus t. Okay, so like we saw last time, The first thing that we have to do to find a general solution of the non-homogeneous equation is solve the corresponding homogeneous equation. So the first step in the outline of the solution for this non-homogeneous equation is to identify that fundamental set of solutions to the corresponding homogeneous equation. Then to solve for the particular solution, we'll go ahead and start with a general similar form of the right-hand side. So the right-hand side is e to the minus t. We'll take a general similar form to be a e to the minus t. Now compare that to the fundamental set of solutions, and what you notice is you can see that that's going to solve the homogeneous equation. So amend our guess, multiplying by t until our guess no longer solves the homogeneous equation. In this case, it just takes once, and take xp to be a times t times e to the minus t. Go ahead and plug that guess xp into our differential operator, hit it with L, and you'll find that you get out 2a e to the minus t. Now what we would like is to have lxp equal to 3 e to the minus t. That tells us that 2a has to be 3, and if 2a has to be 3, then a has to be 3/2. Okay, so that is actually the particular solution of this equation. Xp is 3/2 t e to the minus t, which we can add to the corresponding solution to the homogeneous equation to get the general solution of the non-homogeneous equation. Okay, folks. Hope you've enjoyed this video on solving non-homogeneous differential equations with the method of undetermined coefficients. Again, in this video, we had a look at using the method of undetermined coefficients, which boils down to using a general similar form of the source term, amending that if necessary after comparing to the solution of the corresponding homogeneous equation. Once we have that particular solution, the general solution of the non-homogeneous equation is just the solution of the homogeneous equation plus a particular solution. Okay, next time we'll have a look at some applications of these non-homogeneous equations. Thanks for watching, and so long for now. Bye-bye.